All right, welcome. Today we're going to break down how search actually works for structured documents, like XML files. If you've ever wondered how a system finds not just the right words, but the right words in exactly the right place, then this is for you. Okay, let's just dive right in. So, to get started, let's really nail down the difference between searching a simple text file and a structured XML file. I mean, think about it. With a regular text document, you're pretty much just looking for words. But with XML, say for an online store's product list, you need to know more, right? You got to know, is that word a title, an author, or maybe a price? That extra layer of context is the key challenge we're tackling. So you might be wondering, why can't we just use the same old search methods that have worked for decades? Well, let's take a look at why they kind of hit a wall when it comes to the rich structure you find inside XML. The standard method is something called the vector space model, or VSM. The easiest way to think about it is this. It looks at a document, completely ignores all the order and structure, and just makes a list of what words appear and how often. It's basically a bag of words approach. Super simple, but as we're about to see, it's totally blind to the structure that's so crucial in XML. And this quote just hits the nail on the head. This is where the whole thing falls apart. If we use this simple bag of words model, we get a ton of results that are just wrong. Imagine you're searching for the name Gates, but specifically as an author. A standard system might just throw back a document where Gates is mentioned in the title, which is absolutely not what you asked for. So, if ignoring the structure is the problem, then obviously the solution has to involve understanding it. And this is where things get really cool. A very clever concept called lexicalized subtrees comes into play. Okay, so this is the central puzzle, right? How on earth can we create one single piece of information that captures both the word itself and its unique location within that document's hierarchy? How do you combine the content and the context all in one go? And the answer, the real hero of our story here, is the lexicalized subtree. So it's not just the word Gates anymore. No. It's now something like the path to the author tag /Gates. A lexicalized subtree is a whole new kind of dimension for our vector space. It's one that combines a word with its full, unique path from the very top of the XML document. All right, so that's the theory. But how does this actually work in practice? Let's get practical and see how we actually take an XML document and represent it using this new structure-aware vector space. This diagram here just lays it all out perfectly. Over on the left, you've got this simple XML structure for a book. Now, look to the right, and you can see how it's all broken down. Notice how the word bill that's under the author tag becomes a totally different thing than a word bill that might be under the title tag. Each one of those path and word combinations gets to be its own unique piece of the puzzle. It's actually a pretty straightforward three-step process. First, you go to the very end of each branch in the XML tree, the leaves, and you grab the text. Second, you just split that text up into individual words. And finally, for each of those words, you create a brand new dimension that is that word plus its unique structural path. Okay, so we've done all this work. What's the result? What does this new structure-aware vector space actually allow us to do? Let's see what it builds. And this right here is the big aha moment. We've totally redefined what a dimension even means. In the old model, a dimension was just a word, a single word. In this new XML VSM, a dimension is a lexicalized subtree. It's that word fused together with its structural context. And because we've made that fundamental change, we can finally do what we set out to do. We can represent a user's query and all the documents as vectors in this new, much smarter space. So now, when we compare them, the matches are incredibly accurate because they inherently respect the structure of what you searched for and the document itself. But, there's no free lunch, right? This amazing technology comes with a pretty big trade-off. On the one hand, yes, accuracy skyrockets. We get way more relevant results. But on the other hand, the size of our vector space can just explode. I mean, think about it. Every single word in every unique location becomes its own separate dimension. The system can become absolutely massive and really computationally expensive. And that really leaves us with this big, lingering question, doesn't it? We have this incredible tool for structural search, but it comes at a cost. So the next great challenge is finding that sweet spot. How do you capture just enough structural detail to be super accurate without building a monster of a system that's just too big to be practical? That's the puzzle driving the future of this field, and it's something to think about the next time you search for something really specific online.